thank you. I would like to thank to the organizer for inviting me to speak here. And in this talk, I'm going to talk about presentability of Artin stacks in the C-infinity smooth setting. And this is joint work with Professor Ernesto Lupercio. So, broadly speaking, we can think of or about differentiable stacks as a sort of generalization of the classical notion of a smooth manifold, in such a way that this generalization allows us to deal with equivariant phenomena in an invariant way, or in a coordinate-free way, if you want. So just as classical smooth manifolds allow us to talk about properties or constructions which are invariant on their coordinate change, the notion of differentiable stack do a similar job for the equivariant setting. Okay, so for instance, we can start with the Euclidean category, and by this I mean the category whose objects are open sets in some Euclidean space for varying dimensions, and whose morphisms are just given by C-infinity smooth maps. So this category, this Euclidean category, provides us with a certain sense of what a space is, and we can generalize out of this category, or we can construct out of this category, or we can construct out of this category several possible generalizations to the notion of a space or manifold. So, of course, the kind of spaces that we obtain out of this sort of construction will depend on what we mean by local. So, for example, if by local we mean local in the Euclidean topology, then the sort of spaces that we can construct out of Euclidean open sets are just the classical smooth manifolds. But we have several other options available here. For example, we can consider also the notion of locality, which is provided by étale maps or by local diffeomorphisms. And in this case, the class of spaces that we can get by gluing Euclidean sets in this setting corresponds to the notion of orbifold. More generally, if we now consider the notion of locality given by submersive maps, by smooth submersions, then the corresponding notion of space that we obtain in this last case correspond to the so-called Artin stacks, which is the kind of spaces that we are interested in along the talk. So note that any one of these constructions generalize the previous one. For instance, we have the basic local models, which are given by the Euclidean category, and the category of smooth manifolds enlarge or generalize our notion of space, and in the same way we can also extend smooth manifolds and consider orbifolds, and all of these notions are included in the more general one of Artin stacks. However, let me point out here that even if the two categories which appear there, the Euclidean category and the category of smooth manifolds, are just categories, for orbifolds and for Artin stacks, this turns out to be a very special kind of big categories. In other words, if we consider the collection of maps from one stack into another, then this collection will organize not just in a plane set, but in fact, it will organize into a group point, a discrete group point. So for any pair of stacks, the space of maps will organize into a group point, and in particular, this means that the points of a stack are equipped or are endowed with a with an automorphism group. So in some sense, each point of an stack will comes equipped with a sort of internal symmetry. Okay. So let me consider two very elementary examples of stacks. And whenever we give ourselves a Lie group G, we can construct out of this Lie group a stack which is called the classifying stack of the group. And this stack has the following property, which in fact is the defining property of this stack, which says that for any other stack X, the groupoid of maps from X onto BG is just the groupoid of principal G bundles over X. More generally, whenever we have a Lie group action of a Lie group G on a smooth manifold M, we can also construct the quotient stack. And this is a model, or this provides a model for the orbit space of the group action within the framework of stacks. Now, in practice, we often represent stacks by means of Lie groupoids, where a Lie groupoid is just a groupoid object in the category of smooth manifolds. And this sort of presentation by means of Lie groupoids correspond to the idea of fixing a coordinate system for our space. Moreover, any two Morita equivalent Lie groupoids will correspond to the same stack, and this is analogous to the fact that we are considering properties which are invariant under change of coordinates. So Morita equivalence in this case can be thought as a sort of invariance under coordinate change in an equivariant setting. Okay, now. So note that here we have two extreme cases. On the one hand, we can consider a manifold. Every manifold determines a stack, but these stacks that come from a smooth manifold has no internal symmetries. That is, the points of a manifold, the automorphism group of the point of a manifold is a trivial group. So this is one extreme case, and the other, on the other hand, we can also consider this sort of classifying stacks. And in this case, the classifying stack of a group has just one point, but this point is full of symmetry. The symmetry group of this point is precisely the group G. So we have these two extreme situations. And in the middle, we have we can, and in the middle, it can happen. There is some intermediate situations, just like in the case of global quotient stacks, like the one in the second example. So in fact, it turns out that a general Artin differentiable stack can be constructed out of these global quotients. So the local structure of an Artin stack can be described by means of the so-called linearization theorem due to Sung and Kreinig. And this theorem states that whenever we have an Artin differentiable stack X, then we can always find a covering by open substacks in such a way that each element in the cover is a global quotient stack of a compact Lie group action on a smooth manifold. So these local groups here are compact groups, and these are acting on a smooth manifold. And locally, then an Artin stack turns out to be a local quotient stack. For the case of orbifolds, we have a similar description, but in that case, we can even choose these local groups to be finite groups. Now, a natural question that we can ask in this setting is that is to ask when is X itself presentable as a global quotient stack. That is when we can choose a covering by just one shard of this form, like this. Okay, so for example, you can consider the following situation. For instance, if you consider a weighted projective line that is an orbifold which have two orbifold points, just two orbifold points, and this orbifold can be obtained by gluing together two orbifold shards, but it can be proved that such kind of orbifolds cannot be obtained by just a single orbifold shard. However, even if this is not possible for orbifold shards, that is with finite local groups, these kind of orbifolds, like the weighted projective line, can be obtained as a global quotient stack in the Artin sense. For instance, we can take the action of the circle on S2, a suitable action, circle action on the two-dimensional sphere, and we can obtain the weighted projective line with two orbifold singularities as the global quotient of S2 divided by S1. So it turned to be the case that such an orbifold is in fact a global quotient stack in the Artin sense. In fact, it was conjectured by Moerdijk around the 90s that any orbifold can be obtained in this way. That is, that any orbifold can be presented by means of a compact Lie group action on a smooth manifold. Now, let me mention the cases in which we know that this conjecture is true. But before that, let me just mention that the property of being a global quotient stack can be reformulated in various ways. For instance, there is a reformulation due to Enrique's in terms of the existence of enough vector bundles. And we will say that a stack X has enough vector bundles, finite dimensional vector bundles, if for any open substack like this and a vector bundle defined on this open subset or open substack, we can always find a global vector bundle on the whole X, such that the original vector bundle can be linearly embedded in this global vector bundle. So whenever this happens, we will say that X has enough vector bundles, and Enrique's proved that the property of having enough vector bundles is just equivalent to the property of being a global quotient stack in the Artin sense. Okay, so by the way, this property of having enough vector bundles is or can be thought as a sort of topological analog of Totaro's resolution property in the algebraic setting. And it is known that this resolution property in the algebraic category is also closely related to the problem of global quotient presentability of stacks. Okay, so in fact, this property of having enough vector bundles turns out to be equivalent to other interesting properties of stacks. Let me just mention these three properties. So having enough vector bundles can also be thought as a sort of Peter-Bale property, in the sense that for any Artin differentiable stack X, we have we can construct the so-called universal Hilbert bundle, which is a bundle, a infinite dimensional Hilbert bundle over X, which contains any other Hilbert bundle, and in fact contain infinitely many copies of any other vector bundle on X. So it was pointed out by Fried, Hopkins, and Telemann that that the property of having enough vector bundles and then the property of being a global quotient stack, is in fact equivalent to this sort of Peter-Bale property, which says that the universal bundle can be split as an orthogonal sum of finite dimensional pieces. So, for example, in the case of the classifying stack of a compact Lie group, this property is just is satisfied just by the classical Peter-Bale theorem, and we can also state the property of having enough vector bundles in terms of Fredholm complexes. So an stack X has enough vector bundles if and only if every Fredholm complex, which is a bounded complex of infinite dimensional Hilbert bundles on X, can be is chain homotopically equivalent to a finite dimensional complex. So this is an observation of Siegel in the 70s, and so having enough vector bundles is equivalent to this sort of property, which in the algebraic category is related to the notion of perfect complex. So Fredholm complexes can be thought as the analog of perfect complexes, and this is saying that any perfect complex will be a strict perfect complex just in case X is a global quotient stack. So these two properties, the Peter-Bale property and this Fredholm complex property, are deeply connected with, let's say, some K-theoretic aspects of differentiable stacks or topological stacks. And in fact, this second property can also be thought as a sort of a T-Jajanic property, which relates the K-theory of X defined in terms of Fredholm complexes or Fredholm operators, and the naive K-theory defined in terms of finite dimensional vector bundles. And finally, we can also phrase this property of having enough vector bundles in terms of the Tanakian formalism. So out of the category of finite dimensional vector bundles on X, this is a tensor category. We can endow this with a tensor structure, and by choosing a fiber functor on this tensor category, we can define or construct the so-called Tanakian dual of X, and there is a canonical map from X into its Tanakian dual. So this map turns out to be an equivalence of stacks just in case X has enough vector bundles. So these three properties are equivalent ways or are equivalent formulations of the property of having enough vector bundles, and then are equivalent to the problem of global quotient presentability for Artin stacks. Okay, so now let me mention the cases in which we know that the global quotient presentability holds. And it is a classical result that goes back to Satake in the 50s, that any effective orbifold is a global quotient. And the idea of the proof is very simple. Let me just explain briefly how he proved this fact. And in this case, for the case of orbifolds, we know about the existence of at least one finite dimensional vector bundle, namely the tangent bundle of the orbifold. Now we can endow X and its tangent bundle with a Riemannian matrix. And by doing that, we can construct the associated frame bundle of the tangent bundle. Now, this frame bundle is classified by some map from X into the classifying stack of the orthogonal group of the appropriate dimension. Here, n is the dimension of the orbifold. And this map is a representable map of stacks just in case the original orbifold is effective. In fact, by definition, an orbifold is effective if we can choose an orbifold atlas in such a way that the local groups acts effectively on the corresponding chart. And this is just the same that the condition that for any point on X, the induced map from the automorphism group of the point into the orthogonal group, the map induced from this classifying map is injective. So X is effective if and only if these maps are injective for each point on X. So if this happens, if all of these maps are injective, then the classifying map from X into BG is a representable map of stacks. And this implies in particular that the frame bundle, which is the pullback of the universal bundle on B, on BON, is necessarily a manifold. So the total space of the frame bundle is a manifold, and we can recover our orbifold X by the natural action of ON on the frame bundle. Now, let me just mention that for ineffective orbifolds or non-effective orbifolds, there is previous work of several people. For instance, Enrique and Metzler, Kalisnik, Pronk, and and this work culminates in the work of Pardon, which settled the case of orbispaces. So orbispaces are the topological versions of orbifolds, and for this, for orbispaces with mild restrictions on the growth of the size of the stabilizers, Pardon has proved that these orbispaces are or can be present as global quotients in the Artin sense. On the other hand, it is also known that there are topological obstructions to global quotient presentability for general Artin differentiable stacks. For example, well, this counterexample is due to Enrique's. And suppose that we take the fundamental class of the three-dimensional sphere with integer coefficients, and if this class will define an S1 GERF over S3. So out of this class, we can construct a GERF whose structure group, well, an S1 GERF over S3. And the total space of this GERF is an Artin differentiable stack. It turns out to be an Artin differentiable stack. The stabilizer at any point is just the circle. And it can be proved that this stack, that this Artin stack is not presentable as a global quotient. However, note that the class which defined the stack has no torsion, since it is the generator on this H3, which is just set. So this class which defines the GERF X alpha is defined by means of a non-torsion element. And in fact, I would like to stress or to point out in this talk that this is the only kind of obstruction to global quotient presentability. So in order to explain this, let me briefly recall what is an S1 GERF. So an S1 GERF over a differentiable stack X is just as a certain kind of fibration whose fiber is the classifying stack of S1. So these kind of fibrations are classified by the elements in the second cohomology group of X with coefficients in the sheaf of germs of continuous maps on X with values in S1. And in fact, the notion of GERF was invented in order to provide a geometric realization of these cohomology classes, of this sort of cohomology classes. In this case, in the abelian situation, that is when we have an S1 GERF, we can consider the short exact exponential sequence. And this sequence will induce a connecting map from H2 onto H3 with coefficients in Z. And the class which determines our GERF will then induce a class in H3. And this class is called the Dixmier-Doity invariant of the GERF. Moreover, in this case, the connecting homomorphism is in fact an isomorphism. And then the Dixmier-Doity invariant turns out to be a complete invariant for GERFs, for S1 GERFs. So the question that I would like to address here is, when is the total space of such a GERF, of such an S1 GERF, presentable as a global quotient stack? That is, under what conditions we can guarantee that the total space of this GERF is a global quotient stack. So to do that, let me just mention that there is another way to realize cohomology classes. So the notion of GERF allows us to realize geometrically the cohomology classes in H2, but we can also realize such classes by means of projective bundles. So for example, we can fix an integer n, and let me consider the central extension. Here is the projective group. Here UN is the unitary group. This is the corresponding projective group, and here we have a central extension. And this short exact sequence induce a connecting map in non-abelian cohomology. In fact, if we consider a principal PU bundle over X, that is, let me call this a finite dimensional projective bundle over X, then this this bundle will be classified by some element in H1 in non-abelian cohomology with coefficients in the projective group. And by the connecting map, we can send this class which defines P into a class in H2. So out of this class in H2, we can construct an S1 GERF over X, and then every finite dimensional projective bundle can be used in order to construct a GERF. So in fact, these two notions, the notion of projective bundles and the notion of abelian GERF, turns out to be essentially equivalent in some sense. So, however, note that for these finite dimensional bundles, that is when the bundle P is a finite dimensional projective bundle, the corresponding class in H2 is necessarily a torsion class. And this can be seen very easily by inspection of this diagram of short exact sequence. Here, mu n is the cyclic group of n roots of unity. And in this case, the class in H2 determined by this projective bundle is in fact a torsion class. Okay. Now, the torsion part, the group of torsion elements in H2, is often called the Brouwer group of X, or the Brouwer-Grothendieck group of X. And moreover, we can also consider this exact sequence where Q mod Z is the procyclic group of roots of unity, can be thought as the procyclic groups of unity. And this short exact sequence induce a corresponding Bochstein map from H2 with coefficients in this procyclic group onto H3 with coefficients in Z. And the image of this Bochstein map is, in fact, the torsion part in H3, which is isomorphic to the torsion part of H2, which is just the Brouwer group of X. So, as I said, every finite dimensional projective bundle produces an element in the Brouwer group of X. And then we may ask when when if the converse is also true. That is, if every element in the Bragg group group of X can be realized by means of a finite dimensional projective bundle over X. Okay, so let me so to deal with this sort of finite dimensional projective bundles, it is convenient to introduce the infinite projective group, which is just the limit of these PUNs. And the homotopy type of the classifying space of PU infinity, defined in this way, is known to split as a product of Eilenberg-MacLane spaces, and this is a classical result due to Serre, which ultimately rests on Bott's periodicity theorem. And then we have this splitting of BP U infinity as a product of Eilenberg-MacLane spaces, all in even dimension. And in dimension bigger than 2, the coefficients are just the rationals. So we have this splitting, and moreover, if we denote by Proch infinity of X, the groupoid of principal PU infinity bundles over X, that is the groupoid of finite dimensional projective bundles over X, then this groupoid of bundles is just equivalent to the group of maps from X onto BP, onto the classifying stack of PU infinity. And then, whenever we have a map, a stacking map from X into the classifying stack of PU infinity, we can produce a continuous map from the classifying space of X into the classifying space of PU infinity. Here, the classifying space of X, or the homotopy type of the stack, can be defined or can be constructed in terms of a Lie groupoid presentation. So we can choose a Lie groupoid which present the stack X, and then we can take the check nerve of this Lie groupoid, and this nerve is a simplicial manifold whose geometric realization is by definition the classifying space of X, or the homotopy type of X. So this space, or this the weak homotopy type of this space, is independent on the Lie groupoid presentation, and in fact there are this construction is functorial in some sense. So out of any stacking map from X onto the classifying stack of PU infinity, we can produce a continuous map from the classifying space of X into the classifying space of PU infinity. And this construction induces a functor from the groupoid of finite dimensional projective bundles on X onto the fundamental groupoid of the space of maps. So here, this denotes the space of continuous maps from X into BP U infinity, and this is a functor of groupoids. So we are interested in the question of when is this functor an equivalence of groupoids. And in fact, there are in the two extreme cases of manifolds and classifying stacks of finite groups, this is in fact the case. So if X is a smooth manifold, then the functor, the previous functor that we construct from this groupoid into this fundamental groupoid, is in fact an equivalence of groupoids. And this is just another way to say that principal bundles with the structure group PU infinity are classified by homotopy classes of maps from M into the classifying space of PU infinity. On the other hand, if we now take X as the classifying stack of a finite group G, then this functor turns out to be also an equivalence. And this is because of the following fact. So this groupoid of bundles in fact classifies projective representations of G, finite dimensional projective representations of G, up to conjugation. And on the other hand, the fundamental group point of the space of maps from BG into the classifying space of PU infinity classifies certain central extensions of G and the procyclic group of roots of unity. And this is because since G here is a finite group, then since we have this splitting of BPU infinity, then this part of dimension bigger than 2 will disappear, since there are no cohomology in even dimension for the classifying. A finite group has no rational cohomology. So this the first part is the only part that matters in this case. And then the fundamental group point of the space of maps from BG into this Eilenberg-MacLane space classify, in fact, this sort of central extensions. And in particular, the connected components of the group point of finite dimensional projective representations of G are in correspondence or are classified by cohomology classes in the second cohomology group of G with coefficients in the procyclic group of roots of unity. So in these two cases, we know that this map is an equivalence of categories. And in fact, we can use these two extreme situations in order to prove that this is also the case for general orbifolds. So to see this, in order to see this, let me just mention that in fact this question is a local question. So in fact, if we take an open cover, a cover of X by open substacks, and I denote by this the finite intersections, the k-fold finite intersections of the elements of the covering, then it is enough to prove that the restricted functors on these finite intersections are equivalents of group points. And this is because on one hand, the group point of finite dimensional projective bundles over X can be obtained as the co-limit of the corresponding group points of projective bundles on each piece, and this is just by the descent of maps of stacks. And on the other hand, the fundamental group point of the space of maps from Bx onto BPU infinity is also the homotopical limit of the corresponding restricted group points, and this is just an application of Van Kampen's theorem. Okay, so if we prove that these functors are equivalences for each k-fold intersection, then this will show that the whole functor is in fact an equivalence. However, in the case when X is an orbifold, we can do better. In fact, we can choose this covering in such a way that each UI is an orbifold shard that has a local group, which is a finite group, and also in such a way that these orbifold shards are equivariantly contractible. So in this situation, and also that every k-fold intersection is of the same type. That is, every k-fold intersection of a good cover of an orbifold is an equivariant contractible orbifold shard. So if we choose this cover in that way, then just by this, we can in fact reduce the problem to this case of the classifying stack of a finite group, and then this proves that the map from the group point of projective or finite dimensional projective bundles on X, when X is an orbifold, is an equivalence, is equivalent as the fundamental group point of the space of maps. Okay, now so here we have this result. So when X is an orbifold, the the functor from the groupoid of projective bundles on X is equivalent to the fundamental groupoid of this space of maps. And as a direct consequence, we get the following result, which says that every element in the Brouwer group of X then can be realized as a finite by means of a finite dimensional projective bundle. So every element in the Brouwer group of an orbifold can be realized geometrically by means of a finite dimensional projective bundle. And now let me end just by explaining how this is related to the problem of presentability as a global quotient. So when X, suppose that X is a global quotient stack, and if we take such a global quotient and a finite dimensional projective bundle P over X, then this projective bundle can be realized by means of a G equivariant bundle on M. And moreover, this provides a global quotient presentation of the total space of the bundle as a global quotient stack of this P divided by the action of the group G. Moreover, if we now consider the corresponding cohomology class determined by this P on X, then this alpha will determine a GERF, an S1 GERF over X. And by choosing this presentation of P as a G equivariant bundle, we get a global quotient presentation of the total space of the GERF. And this action, this unitary action on P, is just the action which can be obtained by lifting the projective action of PU infinity on P by means of the canonical projection map. So if we take now this action, this unitary action of U on P, this provides a global quotient presentation of the total space of the GERF. So finally, we can put all this together and we can prove the following statement. So whenever X is a global quotient orbifold, here I need to put on an orbifold. Whenever X is a global quotient orbifold, then the total space of an S1 GERF over X will be presentable as a global quotient stack if and only if the defining class or the Dix-Mier-Doisy invariant is a torsion class. So this then the only topological obstruction to global quotient presentability is, as I said at the beginning of the talk, just given by this sort of non-torsion phenomena. And I think that I stop here and thank you for your attention.